Welcome to the deep dive. So you sent over some really interesting material focusing on dental cements, liners, and bases.
That's right.
And, it might not sound like the most thrilling subject on the surface, but honestly, if you're curious about what really makes dental work successful, this stuff is absolutely key.
He really is.
So our kind of mission today is to try and untangle this world of dental materials. We want to clarify what each thing does, how it works, and, well, why knowing this matters for anyone who's had, say, a filling or a crown.
Exactly. And when you stop and think about it, dental cements are, well, incredibly versatile.
Yeah.
Yeah, the same sort of basic material can pop up in so many different roles, securing a simple filling, holding a big bridge, even sticking on ortho brackets.
Right.
It just goes to show it's not only about the material itself, but how it's mixed, how it's used in that specific scenario.
Okay, let's dive into the fundamentals then. Looking at the chemistry, it seems like most of these cements rely on a pretty basic reaction, right? An acid meeting a base.
That's the core for many of them, yes. You've got a liquid, which is typically the acid, the proton donor reacting with a powder that's alkaline, the base, usually something like glass or metal oxides.
A classic chemical setup.
It is. It's the traditional way these materials harden. But it's important to remember not all of them work that way.
Ah, okay. What are the exceptions?
Well, you've got resin cements. They harden through a process called polymerization. Think of molecules linking up into long chains.
Often triggered by light, right? Like the blue light the dentist uses.
Exactly, or sometimes a chemical activator. And then you have other materials like MTA, mineral trioxide aggregate, which actually sets through hydration. It reacts with water.
So, okay, different paths, but the destination is the same. Taking something sort of paste-like or liquid and turning it into a hard, durable structure.
Precisely. Something strong enough for the job inside your mouth.
And that setting process, that hardening, it's crucial timing-wise, I imagine.
Absolutely critical. The dentist needs enough working time to place everything perfectly, but then it needs to set reasonably fast to, become functional.
Right.
And this whole idea leads us neatly into liners, bases, and even things like varnishes. These are all focused on protecting the pulp, the sensitive inner part of the tooth.
Shielding it from irritation or damage.
That's the goal.
Now, this is where I think it gets a little confusing maybe. It's not always clear-cut like material X is always a liner, is it? It seems to depend more on the situation.
That's a really key point. The clinical context, the indication, is what defines whether something is acting as a liner, a base, or a cement in that moment.
Okay, so maybe we should start by focusing on cements specifically used for luting,
Yeah,
attaching things.
good idea. Let's talk about luting agents.
Right, so luting agents. The sources say these are the materials used to, well, glue things like crowns and bridges onto the prepared teeth. And it sounds like the main way they do this is through mechanical adhesion.
That's the primary mechanism for many, yes.
Yeah.
If you could zoom right in, microscopically, neither the prepared tooth nor the inside of the crown is perfectly smooth. They have tiny little irregularities.
Oh.
The cement, when it's still flowable, seeps into all those microscopic nooks and crannies on both surfaces. Then, as it hardens, it creates a physical interlock, like tiny gears meshing together.
So it's filling those micro gaps for a tight fit. But the sources also mentioned chemical adhesion can boost this bond. Glass ionomers, GICs came up there.
Ah, yes. GICs are fascinating. They go beyond just that physical grip. They actually form a chemical bond directly with the tooth.
How did that work?
The polyacrylic acid in the GIC liquid has these things called carboxyl groups. These groups basically grab onto calcium ions that are present in both the mineral part and the organic part of your enamel and dentin.
Wow. Okay, so it's chemically latching on.
Exactly. It creates a true adhesive bond. And what's really neat is that this bonding process actually continues to develop and strengthen over time as the GIC fully matures in the mouth.
That sounds like a significant advantage for keeping things stuck long term. Now, this term luting interface also came up. What exactly is that?
The luting interface is simply that microscopic space between the crown or bridge and the prepared tooth surface. It's the gap the cement has to fill.
And it has to fill it perfectly, I assume.
Absolutely perfectly. The goal is a hermetic seal. You want zero gaps or voids. This prevents oral fluids, saliva, and especially bacteria from leaking down the sides of the restoration.
Because leakage leads to decay under the crown, right?
Exactly. That leakage or micro leakage is a major pathway for potential problems down the line.
Makes total sense.
Yeah.
Okay, let's shift gears slightly then. What about varnishes and liners? These seem more focused on protecting the pulp directly. Cavity varnish first. Sounds like it's mainly for amalgam fillings.
Yes, cavity varnish is traditionally associated with amalgam. Think of it as a protective coating. It's basically a resin dissolved in a solvent.
Okay.
You paint it onto the prepared cavity floor and walls, the solvent evaporates very quickly, and it leaves behind this super thin resin film.
How thin are we talking?
Very thin, which is why you always need to apply at least 2 layers. One layer might have microscopic pinholes, but 2 layers gives you much better odds of a continuous seal.
And the main benefit. The sources mention reducing fluid infiltration and pulpal irritation based on lab studies.
That's the idea. Amalgam doesn't chemically bond, so there can be tiny gaps at the margins initially. Varnish helps seal those gaps, reducing the flow of fluids that could irritate the pulp.
Right.
There's also a theory that it helps block any potential corrosion products from the amalgam itself from seeping into the dentinal tubules, those little channels in the dentin.
Okay, so varnish is like a sealant, specifically for that amalgam tooth interface. Now, cavity liners. Calcium hydroxide seems to be the star player here.
Calcium hydroxide is a real workhorse for liners, and sometimes bases too. It's valued for a few key reasons. First, it's antimicrobial, which is great in deep cavities where bacteria might still be lurking.
Good point.
Second, it has a high pH, it's alkaline. This can have a soothing effect on an irritated pulp. But maybe its most important property is stimulating secondary dentin formation.
Secondary dentin.
Yeah, it encourages the pulp to lay down a new protective layer of dentin over itself, like building a thicker wall against irritation.
That sounds incredibly useful. But it must have downsides. Lack of strength, maybe?
Exactly. Liners are applied thinly, so they don't offer much mechanical strength or thermal insulation. You can't rely on them to support the filling or block temperature changes.
Okay.
Another thing is that calcium hydroxide is slightly soluble in water. So it's really important it's not left exposed at the cavity margins where saliva could wash it away over time, compromising the seal.
So it's really for those very deep spots right near the pulp. The sources mention pulp capping.
Precisely. Direct pulp capping is when there's a tiny exposure of the pulp itself. Indirect pulp capping is when the decay is extremely close, but not quite exposed. In both cases, you place the calcium hydroxide right over that critical area.
To protect and encourage healing.
Exactly. Protect the pulp, stimulate that secondary dentin. It's also used after certain pulp treatments on baby teeth. And worth mentioning MTA again, that newer material also forms calcium hydroxide and is used for similar pulp therapies, often with better strength.
It seems liners are really focused on that biological interaction right at the pulp interface. So how do cement bases differ?
The main difference is thickness. Bases are applied much thicker, usually over 0.75 millimeters.
Okay, much thicker. Why?
Their main job is providing bulk protection. Think thermal insulation, especially under metal fillings like amalgam, which conduct heat and cold easily. Also protection against galvanic shock, weird electrical currents if you have different metals, and chemical irritation from the filling material itself.
They're more about physical shielding.
Yeah.
And the sources list zinc phosphate, ZOE, some polycarboxylates, and fast-setting GICs as common base materials.
Those are the common ones, yes. In terms of thermal insulation, zinc phosphate and ZOE are definitely better insulators than metal filling.
But not perfect insulators.
No, not like, say, corkboard or something, but they do reduce temperature transfer to the pulp. Other base materials like polycarboxylate and GIC fall within a similar range. It's actually quite complex how heat moves through these layers.
Zinc phosphate got called out as a good thermal insulator, but also for its low pH, its acidity. Why is that a problem for a base?
That's a key consideration. Zinc phosphate stays acidic for a while even after it sets. So if you have a really deep cavity with only a thin layer of dentin left over the pulp,
The acid could seep through.
exactly, it could irritate the pulp, especially if pressure during filling placement forces some acid into those dentinal tubules.
So how do dentists manage that risk?
Well, mixing it thicker to a non-tacky consistency helps because there's less free acid. But often, in very deep spots, the standard approach is to place a thin calcium hydroxide liner first, then put the zinc phosphate base over that.
A layered approach. The liner protects against the base's acidity.
Precisely. The liner acts as a buffer and provides that biological stimulation we talked about.
What about protection against chemical irritation from the filling itself? Do bases help there too?
Yes. Materials like calcium hydroxide, ZOE, polycarboxylate, and GIC all act as effective barriers against potentially irritating components leaching out from the filling material placed on top.
Okay.
And just like with zinc phosphate, If you're using a GIC base in a very deep cavity, putting a calcium hydroxide liner underneath is often recommended as an extra precaution.
Strength is also important for bases, right? They need to hold up.
Absolutely. They form the foundation for the filling. They need enough strength to withstand the forces used to place the filling, and then, of course, the forces of chewing later on. You have to wait for the base to get reasonably hard reach its initial set before packing the filling material on top.
So choosing the right base depends on what factors?
Several things. The cavity design, how deep and wide it is, the type of filling material being used, and, crucially, how close you are to the pulp.
Can you give some examples?
Sure, for amalgam, calcium hydroxide or ZOE are often used as bases, maybe over a liner if it's deep. For direct gold fillings, which need a lot of packing force, you'd want a stronger base like zinc phosphate, polycarboxylate, or GIC, again, potentially over a liner.
And for composites,
Yep.
the white fillings.
For resin composites, calcium hydroxide and GIC are generally considered good base options. And one more thing, if you're using one of those more biocompatible bases like ZOE or GIC under an amalgam filling, you'd typically apply cavity varnish over the hardened base before placing the amalgam.
Okay, that clears up the liner versus base distinction really well. Shall we dive into the specifics of some of these cements now, starting with zinc phosphate, the old classic?
Sounds good. Zinc phosphate's been around forever, relatively speaking. Powder liquid system.
Right.
The powder is mostly zinc oxide over 75%, plus some magnesium oxide. The liquid is phosphoric acid solution, and its concentration is really key. It controls the pH and how fast it sets.
And finer powder sets faster, it said.
Correct. Smaller particles mean more surface area for the reaction.
So when you mix them, what's actually forming? What makes it hard?
The set cement is basically unreacted zinc oxide particles embedded in a hard, sort of glassy matrix of zinc aluminophosphate that forms from the reaction. Water plays a role too. Losing water from the liquid slow setting, adding water speeds it up.
Controlling that working time must be essential. What are the tricks for zinc phosphate?
There are 4 main ways mentioned. 1, use less powder relative to liquid, a thinner mix, but that makes it more acidic and weaker.
Okay, maybe not ideal.
2, add the powder in small bits at first. This gradually neutralizes the acid. 3, mix the last bit of powder for longer. 4, mix it on a cold glass slab.
And that's the best way.
Generally, yes. Cooling the slab slows down the chemical reaction, which is exothermic, meaning it produces heat. So cooling gives the dentist more time.
Adhesion. How does it stick?
Purely mechanical. Zinc phosphate offers no chemical bond to the tooth at all. On the upside, it gets quite strong in compression, it's stiff, and doesn't dissolve easily. But the big downside, as we said, is that acidity. It can stay acidic for hours, even up to 24 hours.
Which is why the liner is often needed.
Exactly. Especially with thin dentin or in younger patients whose dentinal tubules are wider and more open, letting acid potentially reach the pulp more easily. Older patients often have more sclerosis, a natural hardening, which offers some protection.
Got it. Okay, moving on to zinc polycarboxylate. This was the first one with chemical bonding, right?
Yeah.
A big deal.
It was a major step, also a powder liquid system. The liquid this time is polyacrylic acid solution. The powder is mainly zinc oxide again, with some other oxides mixed in. And it does release a tiny bit of fluoride, but much less than GICs.
And that chemical bond, it's the polyacrylic acid again. How does it stick?
Yes, it's the polyacrylic acid. Those carboxyl groups on the acid molecules form ionic bonds with calcium ions on the tooth surface, both enamel and dentin. Enamel bond is usually stronger because there's more mineral, more calcium.
Does the tooth need special preparation for this?
Yes, a super clean surface is critical. Often, the dentist will condition the tooth first with a very mild acid, like 10% polyacrylic acid, for just 10-15 seconds, then rinsed really well. This removes the smear layer, debris from drilling, and keeping it dry and isolated is vital.
What about working time? Shorter than zinc phosphate, I read.
It is generally shorter, yeah. Around 2.5 minutes compared to maybe 5 for zinc phosphate. Cooling the slab can help, but it can also make the polyacrylic acid liquid thicker, harder to mix.
So what's the alternative?
Refrigerating the powder before mixing can slow the reaction without thickening the liquid as much. That's often a better approach.
And its properties? Strength? Pulp response?
Compressive strength is typically lower than zinc phosphate. It's also a bit more elastic, which can make removing the excess cement slightly trickier sometimes. But the huge advantage is pulp response.
Much gentler.
Much gentler, yes. The polyacrylic acid molecules are quite large compared to phosphoric acid, so they don't penetrate the dentinal tubules nearly as easily. This leads to really good biocompatibility, left post-op sensitivity for the patient.
That's a definite plus. Okay, next up, glass ionomer cement, GIC.
Yeah.
You mentioned these earlier, adhesion fluoride release, very versatile.
Hugely versatile. Used for fillings, especially non-load-bearing ones, luting cements, orthoadhesives, temporary fillings, sealants, liners, bases, even core buildups. They're classified into types based on use.
What are they made of?
The powder is a special fluoroaluminosilicate glass. Contains silica, alumina, calcium, and fluoride. The liquid is polyacrylic acid again, but crucially, it also contains tartaric acid.
Ah, tartaric acid. What does that do?
It's a key additive. It improves handling, makes it less viscous, extends the shelf life, gives more working time, but then actually helps it set faster once the reaction really kicks in. It really fine-tunes the whole process.
And the setting reaction itself sounds complex.
It is a bit more involved. The acid dissolves the surface of the glass particles, releasing ions, calcium, aluminum, sodium, fluoride into the water that's part of the liquid. Initially, the polyacrylic acid chains cross-link using the calcium ions. But over the next 24 hours or so, aluminum ions gradually replace the calcium in those cross-links, making the cement much stronger and more stable.
What about the sodium and fluoride?
They don't really take part in the cross-linking, they just get dispersed within the matrix. The final set cement has undissolved glass particles coated in a silica gel, all held in this hydrated matrix of calcium and aluminum polysalts containing fluoride, and it continues to hydrate and mature over time.
Wow. And the adhesion mechanism, also polyacrylic acid.
Yes, similar to polycarboxylate. Chelation between the carboxyl groups and calcium in the tooth's apatite structure. Again, clean surface needed, maybe a pumice clean. Sometimes mild conditioning with phosphoric or polyacrylic acid for 10-20 seconds. Rinse, gentle drying. You don't want to completely dry it out is recommended.
Avoiding contamination is key, I bet.
Absolutely. And again, if you're close to the pulp, less than half a millimeter of dentin left, a calcium hydroxide liner is usually a good idea underneath.
Now, that fluoride release, is it a game changer clinically?
It's definitely a significant feature. GICs release fluoride, comparable initially to the older silicate cements. Lab studies clearly show this fluoride can inhibit demineralization acid attack and even encourage remineralization.
So it should prevent cavities.
That's the hope, especially secondary caries right next to the filling. The in vitro evidence is strong. However, large-scale clinical studies definitively proving GICs are better than, say, composite at preventing secondary caries are still a bit mixed or inconclusive.
Okay.
But that fluoride release is still considered a valuable benefit, particularly for patients who are at higher risk for decay.
Good to know the nuance there. Okay, last one in this category, zinc oxide eugenol, ZOE, described as having a medicament, quality, and neutral pH.
ZOE is unique because of the eugenol, which is oil of cloves. Eugenol has a known soothing sedative effect on the pulp. That's the medicament quality.
Yeah.
And yes, it's usually close to neutral pH, making it very kind to the pulp.
Comes as powder, liquid, or pastes.
Both. Powder is zinc oxide, liquid is eugenol. Or two pastes you mix together.
And how does it set? Not acid-base.
No. A tiny bit of water, usually present in the eugenol, hydrolyzes the zinc oxide to zinc hydroxide. Then, the zinc hydroxide reacts with the eugenol, another chelation reaction, to form the set cement matrix. It's relatively slow setting, but heat and humidity speed it up.
A key point mentioned was about eugenol interfering with resin composites.
Yes, that's important. Residual-free eugenol can inhibit the polymerization, the setting, of resin composites and resin cements. So if you're planning to place a composite filling soon after using a temporary ZOE cement, you should use a non-eugenol zinc oxide temporary cement instead.
Good tip. What are ZOE's main uses then, given its properties?
Well, besides temporary fillings and temporary cementation, it's also used as a root canal sealer and in periodontal dressings partly for its antimicrobial effect. The temporary ZOE cements are great for provisional crowns and bridges for a few weeks.
And implants?
Yes, interestingly, it's often favored for cementing crowns onto implant abutments. It holds well enough, but because it's not super strong, it allows for easier retrieval of the crown later if needed without damaging the implant components.
Okay, that covers the main types in detail. Maybe we can quickly summarize the key takeaways for each cement now. Just the headlines.
Good idea. Zinc phosphate. Long track record, good handling, lasts well if the fit is good. Downsides: pulp irritation risk, no adhesion, no fluoride. But lack of adhesion can help removal. Not great for aesthetics.
ZOE cements.
Biocompatible, soothing. Good for temporary cementation and especially for implant crowns where you might want to retrieve them, but generally weaker and poorer handling than modern permanent cements.
Polycarboxylate.
Key benefits: Kind to the pulp, chemical adhesion. Good for sensitive patients. Downside, short working time limits it mainly to smaller jobs.
Glass ionomer eluting cements.
Lots of pluses. Chemical bond, fluoride release, better resistance to dissolving than zinc phosphate, decent strength though less stiff, often replaces zinc phosphate, good for some ceramics due to translucency, great for ortho bands. Fluoride makes it good for high caries risk patients.
Resin cements.
Yeah.
The modern choice.
Very popular now. Virtually insoluble, tough. Early ones needed bonding agents. Now self-adhesive versions exist. Wide use, especially for less retentive preps and all ceramic restorations needing high aesthetics and strength. Key is removing excess immediately. Lower stiffness doesn't seem to hurt ceramic strength.
And finally, MTA.
Think calcium hydroxide healing properties, but much stronger. Great for vital pulp therapy, endodontic repair situations needing both biological benefit and durability.
So wrapping this all up, it really hammers home that choosing the right material, cement, liner, base, and the specific type within that category is a really careful decision. It's completely dependent on the specific tooth, the specific situation.
Absolutely. It boils down to truly understanding the properties of each material, mechanical, chemical, thermal, biological. You need to know how it's going to behave to get predictable, long-lasting results for the patient.
This has been genuinely fascinating, a real deep dive into something that's so fundamental, but maybe not often thought about by patients. Considering how fast dental materials are evolving, what do you think might be next? What future innovations could change how we protect and restore teeth even more?
That's the exciting question, isn't it? Material science is constantly moving. It's definitely an area to watch.
Indeed. And for our listeners, we hope this has sparked some interest. If any of these areas caught your attention, definitely dig deeper. And if you find more interesting sources or have more questions, please share them with us. We always love having material for another deep dive.